My name is Justine, and I work on building network systems, but I think this talk applies to, ooh, this is pretty echoey. I'm gonna move this down a little bit. I think this talk applies to pretty much anybody who builds software. And in this talk, I'm super open to questions and conversation. In fact, in graduate networking classes, these papers are sort of notorious for leading to arguments and discussion, which is part of why these are two papers that I really, really love. Okay, so we've all had the experience of working with our piece of code, and we start talking about the features that we want. And at some point, we start thinking about how other people or services are going to use our widget. And we usually do this by implementing APIs to talk to these other services. This is actually a very short, narrow view of our piece of software in the world. In reality, it's a small part of this big ecosystem. There are other services that our widgets talk to directly, maybe some extensions up and down the stack. Maybe you're running on one of multiple different platforms that you support. And maybe many, many layers away, there's some human user. So today, we're going to talk about design philosophy. And we're going to talk about principles for thinking about the world outside of your widget, even and especially if your widget is kind of abstract, far down the stack, and invisible from the average human. This is David Clark, and many people in the networking community sort of worship him. He's a research scientist at MIT and well-deserving of the title Internet Philosopher. Most of the seminal work on this topic is due to things that he was involved with. And so today, I recommended 3 papers for the Papers We Love community to read. And upon realizing that I only have an hour to speak, I actually cut one and downgraded it to recommended reading. So today, we're just going to talk about end-to-end arguments in system design and tussles in cyberspace, which is kind of the silliest name ever. All 3 involve Clark as a co-author. As a side note, I met David Clark at a conference once. He told me he liked my talk. It was great. Anyway, before we dig into the papers, I'm going to give some background on what systems folks mean when they talk about layered architectures, because we're going to talk a lot about layers. And we're going to focus especially on the internet, because that's what I and David Clark work on. And for those of you who internet all day, just hang with me while I go through some material that we're all familiar with. So we talk about modular components in systems, and they fit together in layers. One of these famous layered models is the internet model that we see here. At the very bottom, we have our physical layer. This is the part of the system that turns electricity or light or radio into bits. Examples include fiber and Wi-Fi. The link layer is all about turning bits on a wire into messages. You've probably heard about Ethernet. When machines are physically talking to each other on a wire, they're usually using Ethernet. The network layer is the internet protocol. It's the thing that gives us the addresses that allow us to talk across great different distances spanning multiple networks. And the transport layer is the thing that's concerned with connections between hosts. Often the transport layer is responsible for resending data that has been lost or making sure that it doesn't get corrupted or reorder. And at the very top, we have the part that your average Joe actually sees, the tip of the iceberg speaking. We have our application layer, including things like web browsers, email, chat clients, etc. The way these pieces fit together is I'll show through a demonstration. So here I have me and Zishan, and I'm going to send him this sweet paper in a PDF file. At the application layer, I load up my PDF. My application is going to send this down to the transport layer, which establishes a connection and converts it into packets. These packets, it's going to assign some sequence numbers. It's using these sequence numbers to make sure that things don't get lost or reordered. These packets get handed down to the network layer, where we put an IP address on them. That's how we know where to send the data. And then down at the link layer, we hand these packetized objects down to the physical layer, which takes in the bits and ships them across some wires. At the other side, the physical layer hands this back up to the link layer, reconstructs our packets, hands them back up to the network layer. Now we know, okay, this is really me. These are the packets that are sent to me. The transport layer, we double check. Is everything in order? Have I lost any pieces? And then we glue everything back together and hand it back up to the application layer where we can reconstruct our PDF. Sweet. So the internet is just one example of a modular and layered system. Components are implemented independently with APIs in between them. Different layers may have multiple implementations. For example, you have Wi-Fi versus wired Ethernet as your physical layer. And different layers may offer slightly different APIs and different functionality. For example, TCP and UDP are both transport protocols, but TCP guarantees that nothing will get lost and everything shows up in order. UDP doesn't give you any such guarantees. And to make your end-to-end system work, data has to pass through multiple layers. We're plugging all these components together to make our big internet. Now, networks aren't the only systems with layers. People in storage systems draw diagrams that look pretty familiar to me. You have your applications, your POSIX interface, your files, your file system. Somehow some mysterious things happen, and then things get written out to your disk or your solid-state drive. Virtualization, also another context where we run into layers. Your hardware has a kernel on top of it. Your kernel is running a hypervisor on top of it. That hypervisor has some guest kernels, and those guest kernels have user space on top of them again. So there's layers all around us. So today's questions when we're talking about design philosophy is how to not get myopic about living in our own little layer. We need to think about the outside world, and not just about the APIs that we expose to the components we're talking to directly. We need to look all the way up and down the stack, and even up to the users on top. Woo. So without further ado, got some background now, and we can talk about paper number 1. The paper is called End-to-End Arguments in Systems Design. It appeared in November 1984, 3 years before I was born. Appeared in ACM Transactions on Computer Systems, which is kind of a big deal, and it's one of the very influential papers that people tend to read in all sorts of graduate systems classes, networks, systems, databases, et cetera. And the paper starts out with an example that you should now be familiar with now that I've shown you how the internet works. And it involves an oversimplified layer system. We only have 3 components. We have a file system, a program, and a network. And notice that we've now seen diagrams of file systems and networks, and we know that each of these components has lots of layers inside of it. We've collapsed all of that down into just one block. So in this example, we're looking at a careful file transfer. At host A, the transfer program calls upon the file system to read a file from disk, where it resides on several tracks, and the file system passes it to the file transfer program in fixed-size blocks. These fixed-size blocks are then handed down to the communication program. The communication system is going to transmit the file using some communication protocol that involves splitting the data into packets. Packet size is typically different from the file block size and the disk track size. The data communication network moves the packets from computer A to computer B. And at host B, the communication program removes the packets from the communication channel and hands the contained data up to the file transfer application, the part that operates within B. At host B, the file transfer program asks the file system to write the received data to disk. Done. Problem. What if Zishan later reads the file and finds that it's corrupted? What could have gone wrong? Well, it turns out a lot of things can go wrong. The paper lists a long list of reasons. You could have problems in the disk storage system, bit error, whatever, storage. You could have problems in the file system, the file transfer program, some buffer overrun in the data communication system, some error in copying. You could have some bug in the processor, a bit flip in memory. The communication system might drop packets, have corruption, deliver a packet more than once. This is actually a thing that the internet does sometimes. Either the host might just crash while you're in the middle of it. The question is, how do we redesign a system to make sure the file doesn't get corrupted? And to start, we need to know, where do we make these changes? Do we do the changes up at the file system? Do we do them in the program? Do we do them in the network? This is what the end-to-end argument is meant to help us with. And I've added in some red text that I think makes it a little bit more readable. The end-to-end argument goes like this. If the function in question can completely and correctly be implemented with the knowledge and the help of the application standing at the endpoints of the communication system, then providing that question function as a feature of the communication system or lower layer is not possible. However, sometimes an incomplete version of the function provided by the communication system may be useful as a performance enhancement. So let's look at the first part, the if-then, and forget about the however for a little while. If you can implement your function at the end, at the top layer, do it there, and don't do it somewhere down low. Here's why. Let's say that I went ahead and just made a perfectly reliable communication network. I had introduced some sort of network coding or acknowledgments at the network layer to make sure nothing ever got dropped or corrupted on the wire. Well, if we go back to our long list of things that can go wrong, I'm just circling the components that can have problems, not the actual problems that happen. Fixing our errors at this low layer here actually only fixes things for the communication system. It doesn't fix anything going wrong in your processor. It doesn't fix anything going wrong in your disk. It doesn't fix bugs in your code. So it just wasn't very helpful. The paper then proposes an alternative, better solution, which they call end-to-end check and retry. Here's the idea. Our sender is going to read the file in its checksum from disk, and then it's going to verify the file in the checksum, make sure that they match up. Then we send both the file and the checksum. Everything proceeds exactly the same as before. We pass packets down, they get sent across the network, they get reconstructed, and at the other end, when Justine receives the file, he's going to write the file to disk along with its checksum, and then read it back and verify that the two match up. If they match up, we know we're done. End to end, the whole thing is complete, and we got the right file. And if they don't match up, Justine will go back and ask me, can you just resend the file? Something went wrong. Note, by checking at the end, all the way past the finish line, we'll be able to catch if anything went wrong anywhere along the line. And this is the only way to check if there was some sort of bit flip error in writing things out to disk. So we actually would have to do this check no matter what. And if we're doing it here, why bother doing it at a lower layer? So the first lesson is, if you can do it at a high layer, don't bother implementing it at a lower layer. First of all, it's usually redundant. You're going to have to implement it at a high layer anyway, so why bother doing it again somewhere lower? And second of all, they argue that it can often cause confusion. And they give an example of a communication system at MIT where they kept seeing corrupted files. Turns out there was a memory error, but everybody just assumed, well, our communication system is reliable, so we don't have to check anything at higher layers. The paper then goes on to suggest other places that the end-to-end protocol can be useful. Encryption is a really great example here. You ever see all those warnings? Remember, if you're using a VPN, that doesn't mean don't use HTTPS. You still need end-to-end encryption, because just because your VPN offers encryption doesn't mean that the person at the endpoint, the person controlling your VPN, can't see your data. You need HTTPS at the higher layer. Don't give up just because you have your VPN. You also see this play out in the early days of the internet. People often said, well, the internet needs to be really reliable. We need to build a network that guarantees that packets are never dropped, they're never corrupted, that they're never lost. Today's internet doesn't do any of those things. Transport protocols at the endpoints of communication double check if something got lost or corrupted and resend if it got missing. So there's one caveat to this implement everything at the endpoints argument. Sometimes, as a performance optimization, you really do want to implement things at the lower layer of the system rather than at the same time as you're implementing at the higher layer. And that's only when you really, really need that optimization. Consider if all of our loss was really happening at the network layer, and that loss rate was really high. The higher the loss rate in the network, the less likely it is that our whole PDF, end to end, is actually going to make it all the way through. if we have these 5 packets and each one has a 28% chance of loss, that's a really high chance, 68%, that the file won't make it all the way through. So on average, Zishan would have to keep requesting, can you try and send me that PDF again? So as a performance optimization, we might want to bake in some reliability at the network layer, but we should do that redundantly and without forgetting that we have to do it end-to-end as well. Anybody have any other thoughts on where this kind of thing plays out, where you can do a redundant performance optimization in your system? No? Wi-Fi is a great example. Wi-Fi redundantly does retransmission, even though it's sitting under TCP that also does retransmission. That's because Wi-Fi can get really lossy when somebody turns a microwave on. Okay, so far this has been pretty dry. What the heck is this classic networking argument that grad students argue about? There's nothing really to argue about here. Well, that's because the paper, in like the very last section, turns the argument a little bit and tweaks it. And they make a stronger argument. They say, and in many cases, well, it's not just a waste of time to build things at low layers, and it's not just confusing, it's actually really harmful to the internet. Whoa, okay. Here's how that one plays out. Remember our file transfer program that benefited from us adding reliability into the network layer? Well, one way to add reliability is to add some extra bits, like network coding. But that also means that you have slightly less bandwidth coming through your network layer. You've taken up some extra bits. Another way to do that is to use acknowledgements and to withhold packets until you've got all the data. If something goes missing, you wait for a retransmit. And once you've got everything, you pass it up to the application layer, which adds more latency. So this is really not helpful for an application like Skype. With Skype, I really don't want my packets showing up late. Matter of fact, I don't care if all of them show up. I don't care because I'd much rather have a small blip that's over in an instant than receiving everything 100 milliseconds late, but knowing that I got all of it. So this example shows how some applications can actually be constrained by extra functionality that they don't want. In our Skype case, it's that having better latency and bandwidth is more important than getting all the data. So what's good for one context isn't good for everything. And the end-to-end argument, this paper that came out in 1984, was oddly prescient in noticing this problem, because in the internet today, this problem is a huge deal. Here's one example that's super common in enterprises and campus networks today. Everyone's expected to run antivirus to protect them from bad guys on the internet. You know, good guys and bad guys, they look like this. This is an end-to-end solution to network security. We've used the endpoints to protect us from badness. But some people don't always keep their computers updated. And as an optimization, many network administrators want to filter traffic based on what they suspect is malicious and non-malicious to protect these users. And they do this by observing what traffic usually leads to attacks and what usually doesn't. And they tend to be pretty conservative about this. Web traffic and email, it's usually okay. Start seeing IRC, that stuff's dangerous. Strange port numbers, not so good. So it's really common to put some box in your network that enforces this. Only allow web traffic and email. And maybe that's historically all you've ever seen your clients use, and they go along pretty happy because they've got their web traffic and their email, and now all the bad guys are kept out. But then somebody has some cool new app that runs over some high number port number. It's perfectly safe, but it isn't HTTP or email, and now it can't get through our network because we've baked in a security optimization into the low layers of the system. So here's a paper that came out just a couple of years ago, and it proposes that we should now use HTTP for everything. They say that when you have your new app nowadays, firewalls block pretty much everything except HTTP. So you can either go around to every network administrator in the world and ask them to update their firewall policy, or you can just build arbitrary programs on top of HTTP. And so this whole paper is how to build random programs that look like HTTP web traffic that aren't web traffic at all. So despite the good and useful security benefits of our firewalls and our IDSs, they've constrained what applications are or aren't allowed in networks in a way that's not great. Here's another example from the real world. Your iPhone usually connects to web services over LTE or 3G. And this is what we imagine it looks like. But in practice, many ISPs insert content caches to make things load faster for you. So they're keeping copies of frequently fetched data, and instead of you connecting all the way to the web server, you're connecting to their cache, which is 99% of the time a really great performance optimization, because I get super grouchy when my phone won't load Facebook fast enough. But this problem arose when some folks in the UK started designing a new transport protocol. They called it multipath TCP. And the idea here was to send some of your traffic over your LTE connection and some traffic over Wi-Fi, so you get better bandwidth. And then these caches looked at it and said, "What? This looks like a TCP connection, but half the packets are missing. What do I do with this?" Now, they could have just said, OK, well, I'll just let it route through. I won't perform any optimizations. But instead, they just blocked it, and the whole thing broke. So in this paper, the multipath TCP authors talk about challenges they faced when they tried to use their new TCP, this multipath protocol, on the public internet. It just turns out that all of these optimizations that normally had made things faster were causing problems for their new protocol. Luckily, the story does have a very happy ending. The authors developed some workarounds, and multipath TCP now works in your iPhone, so that's great. And this is the part where grad students start to go off the rails. The internet is hopeless. We should not be baking any new optimizations down into the network. And I think most of us have some sort of story where we were being blocked or filtered. We were at a hotel that wouldn't let us use SSH. What's going on? So I'm just going to recap the arguments we've heard from the end-to-end argument, and then I'll take some questions about the end-to-end paper before we pivot into the next paper. The basic argument, the thing that's not so controversial. If you can implement functionality correctly and completely at endpoints, do it there. Don't do it at a lower layer. It saves on redundant work, and it can avoid confusion. But you might, and sometimes you really want to, make exceptions for performance optimizations. Then there's the strong argument. You should really avoid putting unneeded functionality in lower layers of your system altogether. It's harmful, and as many have foretold, it's going to doom innovation on the internet forever. Extra functionality at lower layers constrains how applications can be implemented at higher layers, so we should just avoid it. Okay. That's the end-to-end argument. Any questions up to here? Yes?
Do they talk at all about opt-out functionality? Like if you add extra functionality, make sure you can disable it?
So they'll talk a little bit about that in the next. So the question is, do they talk about opt-out functionality, making sure that if you add extra functionality, can you disable it? In this next paper, we'll get a little bit to that point. Yeah?
In the initial example, you have the file system, the program, and the network.
Mm-hmm.
But if you implemented the verification of the file at the file system, If you implemented verification at the file system there, wouldn't that have the same problem of constraining the behavior, according to the strong argument, of constraining behavior? If you were checksumming at the file system for this particular application?
It's true that I might have some application. So the question here is, this end-to-end communication argument really assumes that the network is at the bottom and that the file system is somehow high layer, and we should be checking things in the file system to do verification. But it's true that in other people's diagrams of the world, the file system is down here at the bottom. And maybe I have some app that's reading in lots of data really, really fast, and it just wants to write out as much of it as quickly as possible and doesn't have time to do verification and checksums, in which case I shouldn't use that version of the file system. So you're right, baking that into the file system from another perspective is actually a terrible idea following the same end-to-end argument. These questions are super tricky. That's a great point. I'd never thought of that one. Okay. So, we've given some good arguments for why you shouldn't bake things into lower layers, and then we've said that for some optimizations, you probably really are sometimes going to want to bake things into lower layers, but it could be harmful. It might not be harmful. Sometimes it's helpful. So who decides what optimizations and constraints are okay to deploy at these core layers of our systems, and what constraints aren't okay? This is what brings us to paper number 2. 20 years after the end-to-end paper, David Clark comes back with his internet philosopher crown. That crown is not actually real, but I would like to give him one. And he says, the internet is not a single happy family of people dedicated to universal packet carriage. What? And here are some examples he gives of our very unhappy family. People want to talk in private over the network, and the government wants to build in some wiretaps at the bottom layers of our system. Conservative governments put their users behind firewalls. Users not only don't like this, but they actually just route around it. They install VPNs. ISPs tell us you can have one host on this network connection, and we're enforcing this by giving you one IP address. And everyone's house has a network address translator with lots of laptops behind it. So in the Tussle paper, the authors call these arguments tussles. It's the ongoing contention between parties with conflicting interests surrounding a mechanism. Different parties adapt a mix of mechanisms to achieve conflicting goals, and others respond by adapting the mechanisms to push back. We need to emphasize the term mechanism here because this is a really interesting conflict in that the mechanism is both the object of the argument and it's something that pushes back on people and makes them change their behavior. Here's a recent example. Back in 2014, there was some controversy about iCloud. Apple had this great iCloud storage system that let you back up your data to the cloud. It was pretty cool. But the government wanted to access that data. They wanted to subpoena information that people were storing in iCloud. So here we had a mechanism, cloud storage, and we had two users. We had all of us who wanted to use it for storage, and we had our government who thought, great, we can use this for legal investigations. But Apple questioned whether or not the government's use of their customers' data was always in the public interest. So they tussled up, and they changed the mechanism. They expanded their encryption feature with the release of iOS 8. So everything uploaded would be encrypted with your private password. So even Apple itself wouldn't be able to unlock the data that it stored for you. So you get to keep your use case, storage, but the government doesn't get to keep theirs, legal investigations. The government didn't like this. Just this year, they tried to push Apple to change the mechanism again by getting them to develop a new backdoor to get them to access the data during the San Bernardino criminal investigation. This tussle is actually still going on. It didn't end. The government got somebody else to build the backdoor, back down on pushing Apple to change the mechanism, but this will not be the last that we hear over this argument over what mechanisms companies are or aren't allowed to implement and what restrictions they can bake into those mechanisms to stop the government from acting on it. So to describe these arguments, the tussles talk about an actor model for tussle. Basically, everybody has their own goals and desires, that everyone is constrained by the system that they're using, and they're trying to use the system to compete, to achieve their own competing desires. So here we have a designer, Claire, whose design is constraining her users, Dahlia and Zishan. So Claire designs, the system imposes some constraints on them, and Zishan and Dahlia are adapting, building workarounds. So they're asking for a backdoor to be built. They're designing a VPN to get around it. Or maybe they're moving to another service. So in response to these workarounds and adaptations, Claire's going to go back and redesign her system, and we go through this process over and over again. Now, note that these redesigns can sometimes extend restrictions, or they can actually help the workaround. I like to think of when people, you remember when we used to write like RT in the retweets and then copy paste somebody's tweet? This was because there was a lack of an ability to coherently link between tweets in Twitter. Twitter noticed this workaround and thought, that's a great use case for our product. This is awesome. And now they have this nice little retweet button. So this tussle can sometimes help people's interests to align, and other times it can bring our interests into this sort of choking collision. And there's an open question about this process. Whether the tussle is going to be driven out of the system, actors are all going to be forced to align, everybody's going to agree, hold hands, go home, or whether this sort of semi-stable dynamic where we just keep adapting and changing and adapting and changing is going to persist forever. So back to design philosophy. We're sitting here thinking about our widgets. We're now aware of Tussle. We're 11 layers down the stack. No one's ever heard of what we're building. And we need to think about how we impact the world around us. How do we design for Tussle? There's two ways to think about designing for Tussle. One is to think about how to stay out of the tussle. Just let people's fights play out agnostically. Just sort of you stay out of the fight. Your system is pure. Another way is to design to influence the tussle. Take a stand. Now, the paper is a little schizophrenic on this issue. It starts out talking about how you should design to stay out of the tussle, build these beautiful agnostic systems. And then it pivots towards the end, and it talks about designing to influence the tussle. So let's first talk about the design principles that they talk about to stay out of the tussle and where they start to pivot after that. So first they say, design for variation and outcome. Do not design as if to dictate the outcome. Stay out of the way. And they propose two rules, two design principles for us to follow: modularity and designing for choice. I'll talk about each of these. First, modular design. Now, my description of modular design is to make the tussle battle somebody else's decision, not yours. And they give two examples, one of bad modularity and one of good modularity. So, bad modularity is the DNS. DNS, for us technical people, is a service ID. You have a bunch of IP addresses. Those represent locations. The DNS is the name of the service. That's it. For the world at large, the DNS is a trademark. It's someone's name. So this international technical organization who manages service IDs is now embroiled in trademark disputes in every country in the world. Here is poor Carly Fiorina, who failed to register her own name. Someone else bought it and set up a website that attacks her. You type in carlyfiorina.com, you get bad news about Carly. So she wants to go to court, and now these poor network engineers at the ICANN are just thinking, I'm just trying to design a globally addressable system, and now I'm supposed to be an intellectual property expert. So this is bad modularity. We've conflated the idea of service ID and trademark. We shouldn't have been in this game in the first place. Here's good modularity. Internet quality of service. The way it works is pretty simple. Here we have our IP header, and we've put in a couple of bits. You put in a number, the lower the number, the better priority your packets get, the better service they get. The higher the number, the less important we assume you are. So, alternatively, we could have removed these bits altogether. Save on bandwidth, we're using less bits, that's great. And then we would just bake into the system. All right, well, VoIP calls are the most important, email is the next most important, and video games are the least important. But then we'd have baked into the system a choice about what is or isn't important, and that's not really our job. Instead, the people who designed QoS said it should be up to the community or the enterprise or the government in that region. Those communities can decide for themselves what they do or don't think is important, and they'll just tell us. They'll give us an ordered ranking, and that's what we'll use to determine quality of service. So this is good modularity here. Now, the other principle they present is designing for choice, letting the user decide. How many of you guys are from the EU? Anybody? Yeah, okay. You recognize this screen? So when you install Windows in the US, you get Internet Explorer. That's it. That's the only option. And the EU said, this is anti-competitive. This is not fair. You have not designed for choice. In the EU, when you install Windows, you get a screen that lets you choose what web browser do you want. And then you just choose whichever. They're all mutually interchangeable, and they install that one for you. Designing for choice, I think, is a little bit easier to reason about than modularity. We're sort of used to thinking about parameterization. It's programming 101. TLS supports multiple crypto algorithms, and so you can choose whichever you want, depending upon who you trust. We all have different email providers. We can run different operating systems, regardless of the hardware that we run. Sometimes it's not quite clear what's the difference between designing modularly and designing for choice. And I think the big difference is really the context in which you apply them in. In modular design, you're concerned about a global decision that has to be made for everyone. For example, those QoS bits. I know plenty of people who would say, I think that my video game traffic is way more important than 911 calls. I do not want to let them design for choice. There has to be a global decision made somewhere. But our architecture that we've designed, the things that we've baked into the low layers of the system, shouldn't assume what that choice is. You should outsource it to something that represents the decision of the community, or the company, or the place where it's being deployed. Designing for choice is what you do when the decision doesn't need to be global, where it's really totally fine that to each his own, everybody does things differently. So the paper goes on to discuss a number of other places where tussles come into play. Here are some examples. Some ISPs ban users from hosting web servers, and so they block port 80. The user solution, obviously, just run your web server on a different port. Residential broadband access, this is another place where they were just like oddly prescient. Here they are back in 2005 saying, today we have about 6,000 dial-up providers in the US, and people have lots of choice about their network provider, but we're worried about this broadband thing. And as somebody who is today, 10 years later, forced to choose between Comcast and AT&T, and that's it, I know that the internet today has not designed for choice when I get to choose between which providers I have. Trust is another place where tussles play out. People want to talk to me, but I don't want them to communicate with me. I set up firewalls, I set up filters, I set up antivirus. The internet is open by default, but how should this mechanism in the middle decide who to listen to? Me, who says don't talk to me, or the person who's sending me all the spam? Anybody think about other systems designed for choice or designed modularly? Anytime you've done it in your own work? Electrical grid. Tell me more.
We're starting to see in some states where we're deregulating, you can choose your electricity provider, but the grid is still owned by the utility. In other states, you have to use the utility.
That's fantastic. I didn't know about that example. That's great.
It's similar to the internet.
Did everybody hear that, the electrical grid? Yeah, okay, that's on the captions. Cool. Okay, so facing all these challenges, the Tussle paper gives us some pretty stern commands. After saying you should stay out of the fight, you should design for choice, you should make it somebody else's decision, they then say there's no such thing as value-neutral design. Don't assume that you know the answer. You're designing a playing field, but at the same time, you can't be value-neutral. So here's the editor's bias. Their bias is that openness, choice, and tussle are good. And they're reacting to a lot of pressures to end choice in the way that we build our infrastructure. There are app stores that restrict what apps you can and can't install on your iPhone or Android or Kindle. There are protocol standardization efforts that have been undermined by governments who want to restrict strong cryptography, preventing our ability to have private communications. There are firewalls, IDSs, and filters that both protect us from badness and implement censoring, filter out competition, and downgrade undesirable traffic. And typically, these are corporations and governments who want to control what's going on. So when the authors of this paper say to design to stay out of tussle, they also are simultaneously telling us influence the tussle in that everyone gets a say. Don't bake in features that you're pushed to do by the government or a corporation or some user who you really like. Let it play out in the world, in the community. They then return to the end-to-end argument, and they say, look, sometimes you're going to have to make some decisions. You're going to have to bake some optimizations or features down into that network layer that are going to constrain the rest of the world. Evolution and enhancement of existing mature applications is inevitable. But you should always be worried about new applications and new use cases. And keeping the net open and transparent for new applications should be the most important goal. And the most that we can do is to protect maturing application, is to bias the tussle, to bias the tussle in terms of continuing to play out rather than stagnating and coming up with some lockdown design that only does one thing that one person has allowed. Yeah, David Clark. So, back to you and your widget. I hope that you're now armed with some design principles. You can look at end-to-end system design to implement complex functionality at the high layers of your system and keep those core low-layer components open and flexible. When you have to make some choices, try to design for choice. Let multiple options be available to your users. And when a global decision does have to be made, design modularly so that your system is agnostic to which decision is made. And different companies and different communities can make their own choices about what is or isn't appropriate to bake into the low layers of the system. Now, if you're interested in reading more on this, first of all, there's the paper that I downgraded, Design Philosophy of the DARPA Internet Protocols. This is a super cool paper. Clark, once again, goes back and reflects on the early days of the internet and the design choices they made. And among other things, it's really interesting to just look at what motivated them at the time. They were super worried about nuclear bombs destroying the internet and not worried about privacy or cryptography at all. Very strange. There are also the other two papers I talked about that reflect on how the internet today is constraining application development. This is HTTP as the narrow waist of the future internet, and the Is It Still Possible to Extend TCP paper. And finally, a very controversial paper, which I think is very cool, is a paper that says that the evolution of layered protocol stacks leads to an hourglass-shaped architecture. There are a lot of different protocols we use for wireless and for wired communication at the physical layer. There are a lot of different applications we run, but there's only one internet protocol. Why don't we have many? This paper tries to answer that question. So, at the end of the day, going back to your super widget, remember, are you giving your users choice, or are you adding constraints? Thanks very much.
Hello, thanks for the talk. In the paper, they kind of criticize DNS and say that it's bad for trademarks or something. What sort of concretely, positively, are they suggesting?
So they don't actually suggest an alternative, which I found really annoying and read the paper. I actually spent some time trying to imagine. You could imagine having some sort of opaque service ID, and then having yet another layer of indirection, where you could subscribe to Google's naming trademarking service, and that would be relevant to the US. And then in China, they would have their own trademarking service that would map to those service IDs. It seems a little hokey to me, actually, but that would be one way to separate those two. I wish that they had given their recommended other example, because everything I could think of to separate those two was a little iffy. Yeah.
Thank you for this excellent talk. I certainly see the value and the philosophy behind pushing things up to the ends. But how do you address for something like, say, TCP and the Zshan sharing network, which we hope will launch this year?
Sorry?
We hope to launch this year.
Oh,
if there's something that every application is going to need to do these things. Even if you say, look, we could solve this at the network layer, but we still have to worry about corrupted hard drives and stuff. So we still are always going to have to do the end-to-end check. But in terms of making 50 different or 1,000 or 1,000,000 different applications all try to get hard things right, how does the paper address, or how do you address that say, like, it's still worth pushing some of these things down to the low level just to make the whole thing more reliable?
Well, so what operating systems do today on this front is actually really nice. Your OS knows about TCP, knows about UDP, and your application is not re-implementing TCP every time. Your application can choose between different transport layers, but the communication layer at the bottom isn't making the decision for you. So they've designed for choice in that way. They've pushed it to the endpoints, but they've pushed it in such a way that applications can plug and play which component they want.
Not all the way up.
Yeah, so not all the way up into software. Great, thanks.